Let us derive the induced EMF equation of a single phase transformer. In this diagram, I have a laminated core, two windings, a primary winding connected to supply having N1 turns. There is a secondary winding having N2 turns which will be connected to the load. In this transformer, supply voltage V1, this is the RMS value of the voltage what I am giving to the primary. E1, it is the RMS value of the induced voltage in the primary. E2 is the induced voltage in the secondary winding. It is the RMS value, and V2 is the RMS value of the terminal voltage which is available at the secondary terminals. Now, when you consider the transformer without load, what we have is the supply voltage V1 will be equal to the induced voltage E1. Similarly, the induced voltage E2 will be equal to the terminal voltage V2. When I give a supply voltage of V1 of t is equals to V1 maximum sin omega t to the primary winding, this winding develops a magnetic flux in the core which will also be sinusoidal. This flux will have an instantaneous value of phi of t given by phi max, that is the maximum value of the flux, sine of omega t. Now this flux will be moving through the core and it will be set up by the primary winding in the core, and this flux links with the secondary winding and induces a voltage. Same lines, the flux produced by the primary winding in the magnetic core links with the primary winding of N1 turns and will give you a induced voltage of E1 volts, which is the RMS value of the induced voltage. If I consider the instantaneous value according to the Faraday's laws of magnetic induction, the instantaneous value of the voltage induced in the primary winding is given by this expression. E1 of t is equals to minus n d phi of t by dt. If I take the value of n1, the primary number of turns, into the differential, I will be getting minus of n d n1 d phi by n1 phi of t by dt, or else I write this equation here, minus d by dt of n1 phi of t. Now this term n1 phi of t, what I have here, this will be the flux linkages in the primary winding. Now this will give you d by dt of n1 phi of t will give you the rate of change of flux linkages in the primary winding. So that will give you the induced voltage. Now the minus sign is according to Lenz's law. It says that the induced voltage, what all you have, it opposes the source of production, that is cause of production of the induced voltage, which is nothing but the supply voltage. So now, magnitude point of view, for the induced EMF, the minus sign is not necessary for us, but here if I substitute the expression for phi of t, what you have, it will be minus d by dt of n1 phi maximum sin omega t. If I differentiate this expression with respect to time, n1 being constant, I can write n1 outside. Phi max is also a constant value. So I have sine of omega t, whose differential is cos omega t, and differential of omega t is omega. Now omega is an angular frequency which is given by 2 pi f, where f is the supply frequency. So therefore I can write this expression as 2 pi f phi max n1 cos omega t. We have a minus sign before this. So if I add that minus sign, I will be getting an expression for the instantaneous voltage as minus 2 pi f phi max n1 cos omega t. Remember here, the voltage what I have given to the primary winding is sinusoidal. The flux produced is also sinusoidal, but the induced voltage what you have in the primary winding, it is co-sinusoidal. So I can modify this expression and write it as 2 pi f phi max n1 sine of omega t minus 90 degree. Now in this term expression, what we have here, this 2 pi f phi max n1 can be written as E1 maximum sine of omega t minus 90 degree. So that E1 maximum, it is the maximum value of the induced voltage. So that is given by 2 pi f phi max n1. Now we can find out the RMS value of the induced voltage as E1 maximum, even RMS value is equals to E1 maximum divided by root 2. This is from the fundamentals of alternating circuits. Therefore, if I substitute the maximum value of the induced voltage, I will be getting an expression as 4.44 F phi maximum N1. So normally when you design a transformer, the maximum value of the flux will not be mentioned, but the flux density value, the maximum value of the flux density will be given. Therefore, I can rewrite the phi max as the expression like this: E1 is equals to 4.44 F B maximum, that is the maximum value of the flux density, AI, this is called net iron area, cross-sectional area of the iron core multiplied by N1 turns. Same lines, I can write an expression for the induced voltage in the secondary. E2 is equals to 4.44 F B maximum AI net iron area multiplied by N2. So these are the expressions for induced voltage in the primary and secondary of the transformer.